So welcome everyone to this last installment of the mini course. So, floor is yours.
Thank you. So I guess I can just start without being introduced, but anyway. Okay, so last time we were talking about the two-point function for long-range percolation. Well, we didn't prove the ZD theorem, we proved the hierarchical version, but the theorem on ZD was that if alpha is less than D, then the average of the critical two-point function over the box of radius r is bounded by r to the minus d plus alpha. And so you'll recall the conjecture is that this exponent is equal to this until it fixates at the nearest neighbor value, right? So, you know, the conjectured curve is like this, and this is the okay. Good. Okay, so and in the course of proving this, or proving the hierarchical version, what we showed is that we studied, well, in the hierarchical version, I was using n to be like a exponential scale. I'm going to switch to using non-exponential scale. So let's define MR to be the Edian largest cluster size in the box. We saw that this satisfies a bound like this. Now, of course, well, we didn't really see this, we did the hierarchical version, but this is true. And in fact, you can deduce this from this as well, actually. So we did things the other way around, but in fact, if you start with this, you actually get a stronger version of this where you can say the clusters can be in ZD, and still their restriction to the box, you still get a bound on the largest one. So maybe let me explain this quickly. So how does that go? Well, here's the idea. If I look at the expected size of the restriction of the cluster at the origin to the box, right? Well, it's at least the contribution I get from the event that the origin is in the largest cluster. So up to some constants, it's at least, well, okay, there's this little slight subtlety here because, you know, the origin is right in the middle of the box. You know, maybe to get this to come out correctly, you should like average the location at the origin on the box, but then by taking boxes that are twice as big and so on, you can go back to just working with the origin, but let me just suppress those details. Morally speaking, what should we get? Well, we should get a bound like this, right? So this is saying, you know, the largest cluster has this size with good probability, right? Because that was how we defined this quantity. So, you know, that just gives you a constant. Now, what's the probability the origin belongs to the largest cluster? Well, it's just going to be, roughly speaking, the ratio of the size of that largest cluster to the volume of the box, right? Which is this term, right? And, you know, if you are in the largest cluster, then it contributes this to the expectation, right? So, you know, we know by summing this, that this is bounded by r to the alpha, right? So then you can rearrange this and get this claimed upper bound. And if you do it this way, you're even getting the stronger thing where the clusters are in the whole space. Of course, it's reasonable to expect it shouldn't really matter, you know, how, if you look at the size of the largest cluster, whether it has to stay in the box or whether it's allowed to go outside the box and back in. It's reasonable that those are the same order. So one thing I should mention is that what does make a huge difference in high dimensions is if you work with periodic boundary conditions. So if instead of working on a box, you work on a torus, it completely changes what happens. So for example, in let's say we're doing a nearest neighbor percolation on ZD, D large, right? I mentioned before that if you have a large box, a criticality, say with side length n, right? You should imagine that there are like a lot of large-ish clusters. So there are roughly n, the d minus 6 clusters of size n to the 4. Okay. And of course, this is nothing like what happens in the critical Shreni graph, right? So, sometimes we think high dimensional things should behave kind of like complete graphs, but that's not what's happening here. But you do recover that Shreni-like behavior if you work on a torus. So on the torus, what happens is all these large clusters, they like merge into order 1 large clusters, and you actually just get order 1 of size n to the d to the 2/3, which is the same as in Shreni. Anyway, this is just an aside to say, actually the boundary conditions are important. In this case, going between what we call free boundary conditions, like saying you have to stay inside the box, versus bulk boundary conditions, meaning you're allowed to go outside and come back in. That doesn't make very much difference, but periodic is a different story, just as a warning. Yep. Yeah, exactly. Or into order 1, many things, yeah. Yeah. Yeah, but yeah. That's how it is. Yeah. Yeah, you should think basically that like when you take this big cluster on the torus, it's like wrapping around the torus a lot. So when you unproject it, like when you take the pre-image from the quotient, it has diameter like much larger than n. Okay. Good. Okay, so so the trouble with this theorem, I mean, it's fine, it's how it's supposed to be, but also with the conjecture, is that there is no distinction in this conjecture between high and low dimension, high and low effective dimension, right? So I mentioned if we look at the 2-point function, we see this kind of graph in the conjecture. But if you look at the volume tail exponent delta, there we expect to see this graph with 3 pieces, right? So we have d over 3. This is, again, you should imagine d is between 1 and 6, alpha c, right? Whereas here, d over 3 is just here or something. You don't see any change in behavior at the 2-point function. Okay, so what we would like to do is go beyond just understanding the 2-point function, try to understand things where this distinction between high and low dimensions is important, and then somehow we have to do something else, right? Now, okay. So maybe I'll start by telling you the theorems. Again. So the stuff I'm going to tell you about now is very recent work. I mean, I just put this on the archive like 2 or 3 weeks ago. Although again, as with this 2-point function story, there was preceding work on the hierarchical model that I did maybe two or 3 years ago, which is similar in terms of the exponents. So maybe I'll start by telling you the high dimensional results. Okay, so as a reminder, as we vary d and alpha, we expect to see all these different regimes, right? So long range, high dimensional, short range, high dimensional, short range, low dimensional, long range, low dimensional. This is marginally short range, high dimensional, long range, critical dimensional, short-range critical dimensional and marginally short-range low dimensional. Okay. And of course, there's this point where they all meet, but that turns out to just belong to this marginally short-range high-dimensional regime. Okay. And basically, what we're going to be able to do is to understand the model in this regime, this line, this regime, this line, and this regime. But I'm going to have to break it up into several theorems because they're kind of different. And the thing to be aware is that the only sort of complicated part of this diagram is that this curve is something that's difficult to understand. I mean, it's not really a curve, right? Because d is an integer, but the values of this boundary between the short range and long range regime in low dimensions is equivalent to conjecturally equivalent to computing the exponents for the nearest neighbor models in low dimensions. Okay. So let's start with high dimensions. Okay, and it's going to turn out that just for sort of technical reasons in the proof, let's extend this line here. So this is the line d equals 3 alpha, right? So down here, this really is the boundary of the low dimensional, high dimensional regimes. Up here, it's just a line that shouldn't really mean anything in the model. And so the theorem is if d is larger than 3 alpha, then first of all, we get the mean field behavior of the volume tail. So in fact, even as a first order asymptotic statement, and we also get convergence to either super Brownian motion or super Levy. What's this? So exactly what this means, I don't really want to go into the definition of what these things are, but what you should imagine is you take the cluster at the origin and you think of it as a measure like this. So it's the counting measure on the cluster. So the scaling limit is going to be taken thinking of the cluster as a random measure. Okay. And then what you need to do, of course, is you need to rescale, right? So rescale space by R. Okay. And then there is some scaling factor. Oh, sorry, I call this zeta R, such that this should be like the typical mass of a cluster when it lives on scale R, so that if you condition the cluster to have size at least this size, then it converges to what it should do weakly. Okay, this thing that it converges to being this super process. And again, actually, the way this comes up in the proof, it's extremely concrete. So really what we prove is we just compute first order asymptotics of arbitrary moments for this. So, actually for the proof, you don't really need to know what this thing on the right-hand side is. You can just think, okay, really the theorem is you can compute the asymptotics of all moments, and then you just have to check that the moments at the right thing. Okay. Good. Okay. So one important thing to stress here is that, unlike traditional approaches to high dimensional percolation through the lace expansion, there are no small parameter assumptions here. Okay, so it does not completely cover the regime that's supposed to be high dimensional because this D larger than 6 but alpha large regime is not treated. But below this line, which includes the whole effectively long-range high-dimensional regime and this whole marginally short-range high-dimensional regime, except for this one point, which has been treated by the lace expansion, I should say, by Chen and Sakai. But in this whole quadrant, which includes a lot of interesting stuff, including many effectively short-range models, it does work for no numerical assumptions. Oh, one thing I should have pointed out yesterday, by the way, when we proved this theorem for the hierarchical lattice, because the hierarchical lattice has so much symmetry, it actually implies the pointwise version. And so I should have mentioned as a corollary of last time is that the triangle condition holds on hierarchical lattice when alpha is less than 2, or equivalently d bigger than 3 alpha. So anyway, I should have mentioned that before. So we had actually already effectively proven mean-field critical behavior for at least one model with a full proof, so that if you ever teach a course on percolation, usually you will decide not to do the lace expansion because it's too heavy for your course. But you can very easily include this proof that the hierarchical model has mean-field critical behavior when it should. Okay, so let's go back to ZD. So this is the high-dimensional theorem. These are not the only things that we prove in high dimensions, and it's sort of a feature of the way we'll do the proofs that you really learn. You learn a lot about the model, and somehow you sort of need to, especially when I'll soon talk about the logarithmic corrections, and somehow to compute these, you have to understand like absolutely everything in excruciating detail. So it's sort of not optional that you have to keep going into every single aspect of what's going on. So a couple more remarks about this. So we also get the asymptotics of this function zeta r. And again, you should think of this as this typical size of large clusters on scale R. Okay. And the asymptotics of this will vary depending on which regime you're in. So I should say, by the way, I said here you either converge to super Brownian motion or the super Levy process. And of course, that's according to whether alpha is greater than or equal to 2, in which case you get Brownian limits, or alpha less than 2, in which case you get these super Levy limits. And this is also reflected in the change in behavior of the scaling function. Let's see. So for alpha bigger than or alpha less than 2, this is r to the 2 alpha. For alpha bigger than 2, to remember how to compute this. Maybe I'll say the other one that I remember better, which is the inverse function of this, and then by writing it on the board, I'll be able to write down its inverse. So another important thing that we compute in this proof is called the radius of gyration. Okay. And let me come back to this like this. Sorry. Should be let's see. Oh yeah, I guess it's just of course it's the same as in nearest neighbor. Yeah. Okay. And there's some log in alpha equals 2, which I should have written down what it is. Log R to something. We'll be able to compute this. Okay. Okay. So basically the point is, we get a very thorough understanding of the model in this regime. So you can think when D is bigger than 3 alpha, or equivalently alpha less than D over 3, you can think that that's when the model is not just mean field, but it's sort of is mean field because the kernel is heavy-tailed enough, right? So you'll remember that we defined the effective dimension to be the max of D and 2D over alpha, right? So, this condition D is bigger than 3 alpha is saying like this contribution to the effective dimension is making you have high effective dimension. Okay. Now, on the other hand, although the theorem is sort of strongest in this regime, we can also prove stuff in the whole high dimensional regime. So, or D larger than 6, and if you just happen to know that you have a bound of the correct order on the 2-point function. So, in particular, if the lace expansion works, if you have these small parameter assumptions that you need to implement the lace expansion, they'll tell you this, and then you can implement the rest of the method, and it gives you these very strong things about like scaling limits and so on, which is stronger than is usually derived from the lace expansion. And there's also a similar thing. If D is equal to 6, and this is bounded by this divided by log, which is again, so if you have D equals 6, alpha equals 2, which is this point here, you can also run this analysis given the appropriate bound on the 2-point function. Morally, you kind of just want to say that the triangle condition is finite, and if you have that instead of this 2-point function, I can prove something very close to this. The caveat is that instead of being a constant here, you get a slowly varying function bounded between two positive constants. That's what I can prove if you just have triangle condition, which of course, for all practical purposes is just as good, but it's like more annoying to write down in the theorem. And similarly, like instead of getting a constant here, you'd get these bounded between two positive constants, slowly varying functions. So, basically instead of what you really want is that instead of just having the triangle condition hold, that the open triangle decays at least like 1 over log or something as you move the points away from each other. Okay, so that's the high dimensional theorem. And I'll actually, I think, be able to tell you quite a lot about how this is proven today. But before doing that, let's talk about the other cases. Okay, so of course, the next thing to do is the critical dimension, right? In fact, maybe let me just modify what I wrote here. Okay, so let's suppose D equals 3 alpha and is less than 6. So that means we're on this line here, right? So we're effectively long range and critical dimensional. Okay. So first of all, we get exactly the log correction. In this case, it's log to the 1/4. Okay. And one thing to stress here is that this is not the same that we conjecturally have for the nearest neighbor model in 6 dimensions, which we should have on this line, right? I mean, we have these two different critical dimensional lines here, and it's perfectly reasonable they have different log powers on them. Okay, and the second part is exactly the same. Except you always get the super Levy process because we're always in. And again, you should just think this means you have the same scaling limit as the branching random walk, and you have to put some appropriate log correction here. And in fact, it's going to be r to the 2 alpha over square root log. Okay. Depending on how fast we go, I may be able to tell you a little bit about where these log powers come from. Okay. What about low dimensions? Well, okay. The difficulty with low dimensions is that we don't really know what this regime is, right? We don't know which values of alpha belong to this regime. That's a complicated question. Okay. So that's not an issue, by the way, in the hierarchical model. There you're always effectively long range, and then all these things can just be done. So the theorem in low dimensions is going to be, and I'll state it vaguely for now, and then I'll come back hopefully and tell you what it means later. So if d is smaller than 3 alpha, and the model is effectively long range. So basically the point is we're going to give a definition of what it means to be effectively long range, and then understand the critical behavior like subject to that condition. And this is something where there's definitely room for improvement in it's a very natural next step to prove that many different definitions one could take of being effectively long range are equivalent. So that's something we haven't really done yet. That would be a nice next thing. But anyway, I won't tell you what this means yet. I'll come back to it later. Then, first of all, the 2-point function is given pointwise by this SAC prediction. In fact, this part, you don't need to be low dimensional. You just need to be effectively long range. And in fact, we prove, it's a theorem, that for d bigger than 3 alpha, this effectively long range condition, which I haven't told you what it is yet, holds if and only if alpha is less than 2, which is what you would expect. So, actually in the high dimensional case, we can even get pointwise bounds on the 2-point function, which I should say somehow our methods are always going to be based around like computing moments. So actually extracting pointwise things from them can be quite annoying. But anyway, in this regime, we can get pointwise estimates. But we can get much more than this. So this is just a long range thing. Another thing is that this volume tail is what it should be, this d minus alpha over d plus alpha, right? That was this. The delta is 1 over the thing in the exponent, right? So we get this exponent. And we also prove many other things. So as I said, somehow everything, the lace expansion is a bit like this as well. Maybe you would just want to prove there's no percolation at criticality or something in high dimensions, but in order to do it, you understand like absolutely everything in excruciating detail, and there's not really a way of doing it where you just get the weaker statement without getting everything. Okay. So another thing, for example, is we also get the 3-point function. So this is another thing where the scaling should not be the same as high dimensions. So, we saw in high dimensions, and this is, a theorem under these assumptions. The 3-point function is of the same order as this tree graph bound, right? Let's say high dimensional long range. So here you get the sum over W of the three 2-point functions. Okay, where these are all like this distance to minus d plus alpha. Okay, and you can actually express this more geometrically. So this is equivalent to saying, if I say d max is the largest distance between the 3 points and d min is the smallest distance, this is the same as taking d max to the minus d plus alpha times d min minus d plus 2 alpha. This is a little analysis exercise. Okay, this is going to be more easier to compare to our other things. Okay, and in fact, in the critical dimension, what do you expect? Well, you should almost get this, but there should be some logs, right? So critical dimensional long range, you'll get the same thing, but divided by square root log d min. Okay. Of course, like which power of log is harder to guess, but Okay. Now, what happens in low dimensions? So there's a very interesting thing actually, and I should say this was a recent development that came not very long before my papers and was extremely useful for many different things. Actually, like in this case, it's just going to give us the upper bound for free, but it's also useful as a way of bounding errors and so on. So there's a very interesting inequality of Gladkov. So this is Nikita Gladkov. He was at the time a graduate student at UCLA, and he's now, I think, just very recently started a postdoc with Hugo in Geneva. And what he showed is that if you have any weighted graph and you look at this the 3-point function, this is always bounded by square root of 8 times the product of the 3 2-point functions. Okay, this is just always true. No conditions. Oops. Do percolation, bond percolation on a graph. If you did site percolation, you have to have a constant that depends on the maximum degree. No. Yeah, he somehow had quite funny motivations for he has papers where he just proves lots of strange inequalities. He just likes inequalities, I guess, and but this one is really interesting, and I think he had a very different perspective on things than other people in the field, I think. And so, remarkably, this is always true, this inequality. And similarly to also the tree graph inequality on the 3-point function is also always true, right, on any graph. And, as I was saying, the tree graph inequality is supposed to be, and, in actually for this model, like provably is sharp in high dimensions and it's not sharp in low dimensions, and it's off by a log at the critical dimension. And the same thing is true with this inequality, but it's sharp in low dimensions and not sharp in high dimensions, but it's always true. Okay. And roughly speaking, like if you're thinking, again, this is just true on any graph, but if you're thinking if you're, any value of beta, sorry, I mean, it's obviously not particular to beta C. But if you're thinking about critical percolation on ZD, you should think like in low dimensions, this, the 2-point function is roughly the product of the two 1-arms, right? So the square root of the 2-point function is just like the 1-arm on that scale, right? So basically, what this inequality is saying is like, well, if you want to connect 3 points, and the more interesting regime is where one of the distance is much smaller than the other two. Basically what happens is that this guy has to pay a 1 ohm on this scale, this guy has to pay a 1 ohm on the large scale, and one of them just has to pay a 1 ohm on the small scale, right? And that's like what, in some sense, what this inequality is saying, but with the square root of the 2-point function rather than the 1 ohm. But again, this picture is only going to give you the correct idea for what the 3-point function is in low dimensions, but the inequality is always true. Okay. And in fact, what we prove, as you're probably guessing, is that this is just the right thing. So in low dimensions, the square root of okay. And of course, you could write this to look more like this if you wanted to. So basically, when we have these three things, we're going to get the large distance twice and the short distance once, right? I mean, that's what we saw in this picture. So you should think this is like d max, the minus d plus alpha times d min to half that power. So minus alpha over 2. Okay, and what you'll see is that when alpha is equal to d over 3, this becomes equal to this, at least if I've done it correctly. So, if alpha is d over 3, this is 1/3 d, right? This is 2/3 d over 2, so it's 1/3 d. So, okay, so what's happening is that at the critical dimension, d is equal to 3 alpha. Actually, the Gladkov bound and the Tregrove bound become the same bound, and they're both wrong by the square root log. Okay. So really, all these theorems, they're not only telling you these things about exponents and so on, but they're kind of verifying a lot of the heuristic picture of what's going on in critical percolation. So in particular, the way you prove these things in low dimensions, it's really showing this kind of hyperscaling picture, i.e. in a box of some size, there's like order 1 large clusters. They're governing most of the interesting stuff. If you have 2 points at some scale, then them being connected to each other is roughly the same as them both being in the large cluster at that scale, all that kind of thing. Also in high dimensions, in the critical dimension, this basic picture of there being this soup of large-ish clusters. In high dimensions, there's a power, many of them. In the critical dimension, there's log many. In that case, it is log to the 1, actually. And it's really telling you a lot more than just these kind of headline results. Okay, so, all right, so at this point, you probably want to get some idea of how you prove things. And I'm going to have to explain how you prove things before I tell you what the definition of effectively long range is, actually, because it's tied up with basically this renormalization group approach that I have. I mean, you use that framework to define this. Okay, so so these renormalization group type things, I was saying earlier about like this Bauer-Schmidt-Bridges-Slade approach, and they have quite a fearsome reputation, I would say, probably even more so than the lace expansion, which itself has a fearsome reputation. But actually, the stuff I'm going to tell you about today, it's not fearsome at all, and I think that will be very clear when I explain it. So we're not really going to need to know any of this other RG stuff, and I didn't really know it myself, so it's certainly not going to be a problem. Okay, so what's the idea? So I have my model's defined in terms of this kernel J, right? Now J was the power at the distance between the two things. It's going to be convenient to use a kernel that's just a rescaling of that, which of course doesn't change anything. And I'm going to think of it instead as the integral from the distance to infinity of the power 1 smaller. Okay, of course I can do that. Okay. Now, I'm going to define what I'll call the cutoff kernel to be the same thing, but where I just integrate to R. Okay, and just for the avoidance of doubts, if these are the wrong way around, you get 0, not a negative number. Okay, I can write the indicator in if you want. Okay. So this is the key definition. Okay, now what's the idea? So now that we've introduced this cutoff kernel, we get the cutoff measures, right? So we now have a 2-parameter family of measures, right? And what I'm going to do is I'm going to fix beta c. Beta c is always going to refer to beta c of the original kernel without the cutoff. Okay, and basically the whole idea of the approach is that you want to understand asymptotics of various things, usually just functions of the cluster at the origin, as R goes to infinity. Okay, and the idea is basically, if you understand the asymptotics of enough things well enough as a function of R, you'll be able to come back and understand everything else. So of course, there are no R's in the theorems, right? So eventually you need to get rid of the R's and prove something that does not refer to them. But that's something you do right at the end. So, basically, almost all the work is going to be going on this side, understanding the behavior of things as a function of the cutoff. Okay, so let's give an example. So to understand the tail of the volume, what that's going to mean basically is understanding just the moments. Right? So can you understand what are the asymptotics of the moments of the cluster? So of course, when I introduce this cutoff, right, it reduces, but because I did it this way with the integral, it actually reduces all of the j's, right? So in particular, it makes the model subcritical, right? So in particular, by sharpness to phase transition, all these moments will be finite. And if I just want to understand the volume tail, it will be enough to understand these volume moments. If I want to understand also the full scaling limit, well, then you need to look at moments that involve something about how the points sit in space. So you could imagine, for example, you would take the sum over the cluster at the origin of maybe like the 1 coordinate of x to the 4 or whatever, and in general, what you want to do is understand moments of this form, x1 to xn, p1. These are all in the cluster at the origin, and these are polynomials, right? It's hopefully plausible that if you can understand the first order asymptotics of arbitrary moments like this, then you understand the full scaling limit. So in fact, the scaling limit stuff, it's not really going to involve anything about superprocesses, or almost. It's really a matter of computing moment asymptotics. But one does have to understand things well enough to check at the end of the day that you got the right moments, right? And indeed, the way these things will work is really you'll establish recurrence relations for these moments, and you have to prove that the superprocess moments satisfy the same recurrence relations. Anyway, so okay. Good. Okay, so hopefully it's at least plausible that we can approach the problem in this way. We can just try to understand lots of moments as a function of this cutoff parameter. Okay, so and it turns out that at least in this case, D strictly larger than 3 alpha, this is actually not so hard to do. There's a nice way of doing it. Okay, now how are we going to understand these moments? So primarily we do it via establishing asymptotic ODEs for these quantities. So let's start with the simplest example, which is just the first moment, the volume. Okay, so what we want to do is differentiate now with respect to R rather than with respect to beta. Okay. Now you'll remember earlier we saw this expression via Russo's formula for the derivative with respect to beta, and there's a similar formula for the derivative with respect to R, which is that it is equal to beta c r to the minus d minus alpha minus 1. Oh, I should say I'm going to just include the convention from now on that my norm actually can be any norm. It doesn't have to be the L2 norm. I'm going to assume that the unit ball in the norm has volume 1. That has the Lebesgue measure 1. Otherwise, you get this constant, the volume of the ball appearing everywhere. Okay. I'll also say BR is going to be the points in ZD with norm at most R. Okay. And this has this scaling assumption implies that this is asymptotic to just R to the D. Otherwise, you get the volume of the ball times R to the D. And in fact, the error here is small by a power. I'm going to cheat to make things a bit easier for myself. I'm going to pretend that it's just equal. And again, the error here is very small, so it's not going to be a problem. Okay. Okay, so going back to the thing. So basically, this term here that I wrote down already, this is the how much, if I have 2 points at distance at most R, what's the intensity at which I'm adding edges as I increase R, right? This thing here is exactly the thing inside the integral that define JR, and then I'm multiplying by beta c because that's how the model works. And then what I need to do is sum over the ball of radius R of the size of the cluster at the origin, the size of the cluster of Y on the indicator that they're different. Okay. So this is very similar to the Russo's formula thing we had before. We're now differentiating with respect to R instead of beta. In particular, the way we set things up with the integral means that as I increase R a bit, every pair of points with distance at most R has the same like weight in the derivative. Okay, good. I should say, the details of how you define this cutoff are obviously not very important, but you definitely don't want to just put an indicator in because then you'll get the derivatives as supported along spheres instead of balls, and that's much worse analytically. In fact, it won't even be differentiable really because of the lattice effect. Okay. So how do we analyze this? Well, the idea is that in high dimensions, when we have these 2 points, have the origin and y, they're typically far away from each other, right, when I'm summing over the ball. These 2 clusters will actually be asymptotically independent. So by which I mean that you should be able to factor this to first order, right? You should get that to first order, where this means that if I take the ratio of the 2 sides, it converges to 1. This should be alpha minus d minus alpha minus 1. I'm going to get the sum over the ball, but that just gives me a factor of, well, the volume of the ball, but I'm pretending that's just equal to r to d. And of course, to first order it is. And then I'm going to get this first moment squared. Okay, and of course I could then cancel this. Okay. Of course, I need to prove this, but let's already comment on, this is plausibly true, right? Like these points are well separated from each other. You're in high dimensions. They should just be behaving independently. Now, this is much nicer than what happens with the beta derivative. So, an alternative approach you might take to all of these things is not introduce this cutoff parameter at all and just say, well, why don't I just study all my moments as beta goes to beta c? And of course, that's a perfectly reasonable thing to do. And if you're able to analyze all of those things, you'll be able to prove everything about the model. Right, but what happens if we look at the beta derivative? Well, in this case, the main contribution to the derivative comes from edges of like bounded length, right? Like small edges. I mean, in high dimensions, it will be anyway. Right, so you have now 2 points that are very close to each other. And of course, what happens in high dimensions, it's still pretty nice. You're getting that these clusters don't interact very strongly with each other. So, maybe this expectation is of the same order as if they're independent. But, actually saying that they're asymptotically independent is way too strong because they're like a fixed distance from each other. I mean, they interact in some non-trivial way, right? So, what would happen there is what should be true. In fact, as far as I can tell, this has not been proven, but something similar was done for self-leading walk, and you should be able to prove this using the Lace expansion, is that there's some limiting constant making this true as beta goes to beta c. But this constant will be something very complicated that's telling you about all the microscopic interactions between these 2 neighboring clusters. If you could do it with the Lace expansion, it would probably give you some infinite series representation for this constant. On the other hand, the limiting constant here is 1 or beta c or whatever. It depends how you want to think about it. The point is, because we really get asymptotic independence, something much simpler is happening in the ODE. Okay. Now, in fact, what happens, though this is much harder to prove, is that this holds even in this critical dimensional case. So in fact, that will, again, it's much harder to prove that it holds. But all of this analysis we're going to do, to first order, we're going to get the same things in the critical dimension as in high dimensions. So, if you're doing beta derivatives, there's no hope here because, in the critical dimension, these 2 things are okay, they're pretty weakly interacting. You get some logs or something, but, this should no longer be a constant. It should be some polylog. And, this is something much harder to understand. But in the long-range model, when you do things with the cutoff, you still get asymptotic independence even at the critical dimension. So it's really makes it, for that reason, much easier to understand what's going on at the critical dimension. And in fact, eventually, all the log corrections and so on, they'll actually come from understanding the second order corrections to these asymptotics rather than in the first order. Okay. Good. And in fact, even in low dimensions, you get this sort of bounded dependence type thing where actually this is the correct order still, even though it's not. So that's that thing of whether these two clusters are boundedly dependent on each other, that's no longer a distinguishing feature between high and low dimensions. Okay. So, let's see how I'm doing for time. Okay. So what I want to do next is actually prove that this is true. So in high dimensions. I'll prove that it's true for D strictly larger than 3 alpha, I should say. So what's the idea? Okay, so let's take this exact expression. Okay, and I'm going to write this. I'm going to write that it's equal to what I want it to be. So again, I'm pretending the volume of the ball has volume exactly after D for simplicity. Times an error term, right? So I'll call this, and I'm going to temporarily work with beta that might not be beta C, so I'll say beta is less than or equal to beta C. Okay. Okay, certainly I can do that if I want. Okay. Now, claim 1, which is always true, is that this error is non-negative. Okay, why is that true? Well, it's just the same thing we saw before, right? So when I proved the mean field lower bound on the susceptibility, right? We proved this differential inequality that was, in that case, it was for beta. But the point is, these two clusters, when I restrict them to be different, they're stochastically smaller than if they're independent, right? So that means that this expectation is bounded by what it would be if they're bounded above by what it would be if they're independent, which is exactly this claim. So that's fine. Okay. Now, claim 2 is that the error is bounded by the ratio of essentially the third moment. So actually, when we apply this, we'll just bound this by the third moment times r to the d times the first moment squared. Why is this true? Well, here's the idea. We're just going to do this very useful sort of silly trick that we write this indicator is 1 minus the other indicator, right? Okay, so if I take this and I write it this way, so I get, I'll do it for, yeah. So I have this term minus this term. Okay. Now this guy, I can use Paris FKG, right? These are increasing functions of the configuration. So this is at least R to the D times the square of the first moment. And this term here, on the other hand, well, I'm summing over points y that are in the cluster. So these two clusters are the same, and I get exactly this thing that I wrote down. Right, and then, okay, this particular bound is because I wrote the arrow in multiplicative form, so I have to divide by the leading order term. Okay. Is that clear? Now, the way we're going to use this is, well, first of all, of course, I can bound this intersection just by the size of the whole cluster. You know, the fact that I have the intersection is sometimes important, but it's not going to be important in this regime D strictly larger than 3 alpha, so let's just ignore it. And then I'm going to bound the third moment using the tree graph inequality. Right, so what I get is this is bounded by 3, and then remember the tree, so the tree graph inequality said that the third moment's bounded by 3 times the 5th power at the first moment. Right, so I'm going to get 5 powers at the first moment in the numerator, 2 in the denominator, so I'll be left with 3 in total. Okay. So let's now see why we're in a promising position to go forward. Okay. So what is this ODE that we're eventually, what we want to get, right, is that this goes to 0. Okay, if the arrow goes to 0, I get my asymptotic ODE that I want. So, you know, what is this ODE that I want? Well, it's F prime is asymptotic to beta C R to the minus alpha minus 1 F squared. So let me just briefly talk about this ODE. So in fact, you know, earlier on, we were looking at this ODE like F prime is bounded by constant times F squared, right? Or is equal or whatever. So of course, this is very similar, but now I have this power of R here. And you should think that, you know, previously we were sending beta to beta C, and now we're sending R to infinity, right? So, you know, and at some point we're going to have to use that we're at criticality, right? If we or something like that, right? So, you know, how are we going to use the fact that we're at criticality? Well, the critical point is exactly the point where this first moment is finite for every R finite, and it tends to infinity as R tends to infinity. Right. Actually, in one dimension, that would also be true for supercritical, but so this is not the only way we're going to use the fact that we're at criticality. Okay. So if you look at this ODE, well, we can solve it by the same method. I mean, this is a separable ODE, so that it's a very standard thing to solve. But let's do it with our trick with the 1 over F, because that way of doing it's very robust to the introduction of errors, right? So, you know, if we actually had equality here, right? We can solve this the way we were saying before, right? You take 1 over f prime. This is minus f prime over f squared, which is equal to minus beta c r to the minus alpha minus 1. So if you integrate, right, you get that 1 over f is constant, easy to forget, as we all know, minus or plus rather beta c over alpha or minus alpha. Okay. And we know we're interested in the solution that goes to infinity as r goes to infinity and not before. So that means actually this constant should be 0. Okay. Good. So you would get that f is okay. Now what you can see is that this solution is, as I was saying, it's very robust to the introduction of errors, right? Because if I have some error here that depends on r, well, I just get it here, right? Right, and then I'm just integrating the error. So this all works out very nicely. So in particular, if I know that this holds asymptotically as r goes to infinity, and that the function has this property, so it blows up at time infinity, not before, then this is actually asymptotic to this. Okay. And moreover, even if it's not asymptotic, even if this is just like, in some interval, sorry, I didn't leave myself enough space there. Plus an element of some interval or something like that, then you'll get that this is also equal to this times some small interval around 1, right? So generally this way of solving the ODE makes it clear that this particular ODE is very robust to the introduction of errors. Okay, now that is not always true. So later we'll come back to some other ODEs. So if you have if you know that a function satisfies the first order asymptotic version of an ODE, it certainly does not always mean that the function is asymptotic to the solution of the ODE, right? But for this one, it does. Okay.
At the beginning, you let beta be free.
Oh yeah, sorry. Here my discussion was, I haven't used it yet. Yeah, sorry. This is going to be in a minute. You'll see it in a minute. Okay. So okay. So the point is, if the error is going to 0 and I'm at criticality, then my expectation will be given to first order by this formula. Okay. Now, what happens if it's given to first order by that formula? Well, then in this bound, I would get, well, r to the 3 alpha in the numerator and r to the d in the denominator, which of course goes to 0. Now of course, this is a circular reasoning, right? I'm saying like, if the error goes to 0, then the error goes to 0. But something actually quite nice is happening, which is that if the error is going to 0 at all, then it goes to 0 at least this fast, right? And when you see yourself getting into this kind of situation where you have a kind of dichotomy between two different possible behaviors, like, it's saying, even if I just had some very, very weak bound on how fast the error goes to 0, then in fact it must go to 0, at least like some power of r, some specific power of r, even with specific constants and so on, right? Then you should think, I might be in a good position where I can apply some kind of bootstrapping analysis. Okay, so, and indeed for this particular problem, there's a very nice way of doing it. Okay. And this is where we'll use, as we often do in these bootstrapping things, the way you do it is by working at subcritical and proving some uniform estimate. Okay, so I know if beta is actually less than beta c, then the limit as r tends to infinity is, well, it's finite, right? Because it's just this. Okay. So what I'm going to do is I'll define r naught of beta to be the supremal value of r such that this expectation is at least twice what it should be at criticality asymptotically. Okay, and I know just because this is actually not blowing up, right? That r naught of beta is finite for beta strictly less than beta c. Okay, and then what I want to do is deduce that it's not just finite, but it's actually bounded in a way that doesn't depend on beta, and then I can take beta up to beta c. Okay. So how's that going to work? So, okay. Right, and the relevant ODE lemma that we can extract from this discussion before is to say, let's say if f prime is at least, I'm making up the constants here, but I'll be careful that there's enough room that they'll be true. So if this holds and f does not blow up, and f of r is finite for all r, let's say for all r bigger than some number r, and f of r is finite for all r, then f is bounded by 1.1 times alpha. This comes from this analysis that we're doing before. Okay. But again, these constants are made up, but I'm just I'm giving myself enough room that they remain true. Okay. Okay, so let's see. So if r is bigger than r naught beta, right, then what do we learn about this error term? Well, it's smaller than some constant, which is actually explicit, but let's not worry about it, times r to the 3 alpha of r to d, right? It's just by definition of, you know, if we're above r naught, we satisfy the right kind of bound. Okay, and so in particular, there's some constant that we can define. So, you know, there exists, let's call it C1, C2, such that if R is bigger than C2 times R naught, then this error is smaller than 0.0. Okay? You know, that's just a trivial thing, right? In fact, yeah, we could take a maximum here instead of a multiplication, doesn't matter. Okay, that so far completely trivial. Okay, now what about if R is smaller than R naught? Well, what we're going to do in that case, we'll just use the fact that the susceptibility, the first moment, is monotone, right? So I'm just going to bound this by some constants, I guess it's C3 times, I'm just going to use the value at R naught in the numerator, right? Which is R naught to the 3 alpha. right? And then in the denominator, as before, I get R to D. And the key thing, basically, is that this will be small even when R is significantly smaller than R naught, because the power here is larger than the power here. Okay? So what that means is that there exists another constant, C4, such that, and an epsilon positive, such that if R is smaller than R naught, but it's bigger than C4 R naught to the 1 minus epsilon, where epsilon is going to be like, D minus 3 alpha or something, then I also have this. Okay. So again, the fact that this is a power is not particularly important, actually. I mean, it's, if you were only winning a log or something, it would also be fine. I mean, you'd have to use a different function here, but okay. Okay. So what do we learn? Well, what this means is that if R is bigger than the maximum of these two things, sorry, the minimum of these two things. Right? Or in fact, let me just say, there's some constant C5. So the constant management in this proof is a bit annoying. There's some constant C5. So that if R is larger than C5 times R naught to the 1 minus epsilon, then this error is small. Right? Just because we have the two, the two cases and they overlap. Okay. So, well, if the error is small, then we can use our lemma to analyze the OD, right? This lemma here. So what we get is that the expectation is smaller than 1.1 alpha over beta c at the alpha for all R larger than this. Right? But this is less than 2. So in fact, I must have that R naught is at most C5 R naught to the 1 minus epsilon. Okay? But now I can rearrange. So R naught is bounded by C5 to the 1 over epsilon. Okay? Now, the point is all these constants we picked, they don't depend on beta, right? So now I get this uniform constant that holds for all beta strictly less than beta c, and then I can just take the limit. Right? So what I deduce is that taking the limit, R naught of beta c is also less than this. So it's fine. Okay. So what I've shown is that, that actually for large enough values of R, the susceptibility is at most twice what it should be, given by the asymptotics. But then I deduce that the error goes to 0. So in fact, it's exactly asymptotics what it should be. All right. Any questions on that? So this is somehow really the key argument that, often with these things, the hardest thing is computing one thing, right? So now we have the dependence of the first moment on R. And from now on in the analysis, we're not really going to have to do this kind of careful, like real analysis type proof. We're more just going to be free to compute things. And when we encounter more errors, we'll be able to show they're small just because we already know the order of one thing. Like we won't have to do this bootstrapping analysis again. Okay. All right. Last chances for questions on this before we move on. And again, you know, the fact that we get this asymptotic formula for the moment with explicit constants, I mean, this is really something that does not happen for the nearest neighbor models. And it also wouldn't happen for the long range models if you did the beta goes to beta C, but no cutoff asymptotics. Okay. By the way, it's a funny thing to mention maybe before I go on. So I mentioned, you know, in the, what happens in the critical dimension is that, you know, there, of course, 3 alpha is equal to D. So if you just use this bound, it's actually not sufficient, right? The error won't go to 0. And the point is, at the critical dimension, the tree graph inequality is off by some log factor. So, you know, you need to prove something like that the tree graph inequality is wasteful by a divergent factor if you want to prove this works at the critical dimension, which is, I'd say, that proof is by far the hardest thing that I do in this series of papers. On the other hand, if you worked with a slightly different kernel, like let's say, you know, instead of right, so the critical dimension is when alpha is d over 3, right? So this one's very hard to understand. But if I add some, if I just make this larger, maybe by this or something, then this proof actually works. If you make it larger by any divergent factor, then you can still use this proof in the critical dimension. And so I have to work extremely hard to deal with exactly this power, but anything larger, this argument still works. And of course, you know, if you actually add a power of log here, then you risk changing the log corrections for the model. But you know, if you add a log, then of course you're not going to really change anything important. I mean, this factor, whatever it is, will be replicated everywhere throughout the analysis. But anyway, okay. And conversely, I should say, if you have anything divergently smaller than this, then I don't know how to prove anything. So, so it's only the exactly this order that the hard argument works for. Okay. Good. Okay. So let's see what we do after we've got the first moment. Okay. So and now that I've got this bootstrapping argument out the way, I'm never going to have to work with subcritical beta again if I don't want to. So let's just go back to beta C. So, you know, let's look at higher moments. And the appropriate formula here is following. So I'll get this to the k, the p minus k plus 1. And this just comes from more or less the exact same reasoning as the first moment derivative formula. So, you know, for example, if you're looking at the second moment, it's the same as the sum of the 3-point function, right? So you have 2 points you want to connect to, right? You're looking at pivotals for connections to both points. And, you know, that pivot, it could be that these 2 points are connected to each other and the pivotal is here. It could be that the origin is already connected to one of the 2 points, but not the other. And you have some pivotal here or vice versa. So, you know, if you look at the second moments, e.g., you'll get 3 C alpha minus D minus alpha minus 1 first moment times. Okay, where this factor of 3 is just coming from the 3 different combinatorial possibilities. Oh, yeah, sorry. Oh, yeah, I always forget to do that. Yeah, thanks. Okay. Right. Again, where this 3, there's the third combinatorial possibility, which is like the pivotals here. Okay. So, in general, you get these binomial terms because you have to choose which of the points are on which side of the pivotal, right? Okay. Good. Now, what you can do in high dimensions, again, and again also at the critical dimension, is that you can prove, and now it's fairly easy actually, because we already showed the correct order of the first moment. We can just use tree graph and so on to bound all the errors. I won't go through it in detail. Is that these asymptotically factorize. So that again, the 2 points, the 2 clusters are behaving asymptotically like they're independent. And so if you look at this moment, it's asymptotic to beta c alpha minus alpha minus 1 times this sum. And of course, really, you prove this by induction, right? I mean, you're kind of computing moments one at a time and then justifying the next ODE using the fact that you already computed lower down in the series. Okay. In particular, when you look at this p equals 2 case, you're going to get 3 beta c alpha minus 1 first moment times second moment. Okay. So, what do you do now? Well, again, you're going to run into this issue, like if I have a first order ODE, what can I say about the solution? Does it have to be asymptotic to the solution of the normal ODE? And as I said, the answer is not always. And it turns out that there's actually different behavior as you change p. So when p equals 1, well, first of all, you'll see that p equals 1 is special because that's the only case you get a nonlinear ODE in the thing that you're differentiating, right? The remaining ones are all linear. And it turns out that the p equals 2 one behaves very differently than the p greater than or equal to 3 ones. Okay, the p equals 2 one is basically just this ODE. Okay, because we can sub in our asymptotics of the first moment, right? And it turns out that satisfying this ODE, you should think this is like the differential version of being a function of regular variation of index 3 alpha. So just to remind you what is regular variation. So we say a function, let's say positive function on the positive reals, is regularly varying if the limit as x tends to infinity exists for all lambda. Okay, and it turns out that if it exists, okay, the function needs to be measurable or something as well for these theorems to be true. Let's say all our functions are measurable. In fact, they'll be like continuous for us. So if you're regularly varying and continuous, say, then in fact, this limit has to equal a power of alpha, right? And this a power of lambda, sorry. Sorry, this is not the same alpha. Let me call this A. Has to be some power of lambda, and this is called the index of regular variation. okay? And regular varying functions with index 0 are called slowly varying functions. So that means f of lambda x over fx tends to 1, which is like a logarithm, for example, is a slowly varying function. Okay, now the only thing essentially that this asymptotic ODE tells you about the function is that it's f is regularly varying of index 3 alpha. Right. So for example, if you have r to the 3 alpha times some log or something, this will satisfy this this ODE. So just having this doesn't really tell you what's going on at the subpolynomial level. Okay. Now, this is actually sort of a good thing in that we know, what I told you is that these things are actually valid at the critical dimension. Eventually, at the critical dimension, we have to encounter some logs, and indeed, this is where we will encounter them. Okay. Now, on the other hand, let me just check the time. Sorry. Once we go to the higher moments, we actually have a different behavior at the ODE, and we can no longer produce any new log factors. So basically, the difference is, in this second moment, we just had one term, right? We have this sum, and we have a 1 and a 2 minus, is that right? 2 minus 1? Those are actually, I think I might have missed a term off my sum, maybe. In any case, whatever the correct thing is, we only get the first moment times second moment. We get a factor of 3 because there are like 3 different ways of getting it, but we don't have any additional things. Whereas once we get to the third moment and higher, right, we'll have a term that's like the first moment times the third moment, but we'll also have a term which is like the second moment squared, right, that comes from the middle choices of k in our sum. Right, and it's basically the presence of this other term, which of course, by the time we're getting to analyzing the third moment, we've already analyzed the second moment, right? So we have this term that we sort of already understand. And this is really changing the behavior at the ODE. And so here's the relevant ODE fact. So suppose you have a function f, it's differentiable, and it satisfies the asymptotic ODE. F is asymptotic to AF plus H over R, where H is regularly varying of index B. Okay, so the claim is that under this assumption, F is also regularly varying of index the maximum of A and B. And if B is strictly larger than A, then F is asymptotic to H over B minus A. Okay. So, this is an elementary thing to prove, right? I mean, but basically, if you want to prove it, just write this down, give the error a name. You've now written this as an inequality. It's a first order linear ODE, so you can just plug in there's an explicit solution with all these integrating factors and so on, and then you just have to extract the asymptotics. Okay. Okay. So the key thing here is that in this case where B is larger than A, so basically what that means is that you have this kind of self-referential term in terms of the function that you're differentiating, and you have this other, what I'll call the driving term. In the case where the coefficient of this self-referential term is not sufficient to cause the function to grow at the rate that it should be growing, then you have to actually be like pegged to the value of H in this simple asymptotic relationship. You can imagine, by the way, in the case where B is equal to A, you get log corrections that you can also analyze explicitly in many cases just using the ODE technique. So this is exactly what happens when we go to the higher moments here. And so what happens is that these, the high moments are basically getting pegged to the value of the second moments, okay? And once you've established this, what you get is that the pth moments is asymptotic to 2p minus 3 double factorial times, I'm running out of space here. Yeah. Times the ratio of the second moment to the first moment to the power p minus 1 times the first moment. Okay. So basically, once you've proven this, you know, and you know that the first moment is explicit, the second moment you know is regularly varying of index 3 alpha, then you just apply this fact inductively. You're always in this situation where A is smaller than B. And then actually the only difficult thing is that you get a weird recurrence relation for the double factorials that you have to figure out why the double factorial is the solution to that recurrence relation. It's not the obvious one that you just multiply by the next odd integer. But you know, you can do it. And you know, in retrospect, somehow I didn't realize this when I was first doing this. You know, there's a very good reason you get this. Of course, this double factorial, we also saw it in these tree graph expressions, right? So basically, this fact that you're seeing double factorials is giving you like a first hint that you're seeing some super processes in the scaling limit because you're getting these moments that are expressible as sums over trees. So, sorry, was there a question? So, oh, sorry, I just didn't write them. Okay. So another way you can think of this asymptotic formula, saying if you look at the size bias distribution, and then you normalize it to have mean 1, then you cancel off all of these terms, and it's just saying that the moment converges the double factorial. So in other words, that size biased normalized random variable is just converging to a chi-squared random variable. Okay. Good. So, you know, so somehow, again, what's happening is that the difficulty is mostly in the first couple of moments, and then everything works beautifully. Okay. Good. All right. So okay. And you know, eventually in the critical dimensional case, you have to compute what this is, but that's something you can do like after you do all this analysis. Okay. So let me next say a little bit about the moments that involve distance, like Euclidean stuff. Okay. So it turns out, you know, this transition between the effectively long range, effectively short range regimes, something you can also understand in terms of this lemma. This ODE lemma is like the workhorse of the whole thing. Okay. So let's suppose we want to understand let's say we sum over the cluster and we want to take like a coordinate. Right? Well, actually, any guesses of the value of this expression? Oh, this thing. Yeah, there's something over the cluster of the x coordinate. X is a bad name, right? But yeah, good. This is 0, right? This is by symmetry, right? If I just take a linear thing, I get the same contribution. You know, if I put a minus here, it's equal to itself. So okay. This is not the first good thing to look at. So let's look at this. Okay. All right, so, we can do something similar to what we did before, right? So we have the origin, we have X, and we have some pivotal edge, right, between them. Okay. And I'll skip the details of the derivation, but basically you can do something very similar to what we were doing before. And what you're going to get is that in high dimensions, this is going to be asymptotic to, and the additional technical difficulty here is that when you basically you want to write X as the sum of these three things, right? So let's say A, B, X, right? You're also going to have to show that the cross terms are negligible, and that's an additional technical thing here, but they are negligible, right? So roughly you're going to get the same thing as if you just had the sum of A1 squared plus A minus B plus coordinate squared plus the cross terms, but again, those just produce lower order things, which again, if things were independent, then you would just, the cross terms would give you these linear things, which would be zero by the same symmetry thing. So the right analog of them being asymptotically independent is just that those cross terms vanish, right? And so what are you going to get? You're going to get 2 from these two things times the expectation times, sorry, r to the minus alpha minus 1 times this quantity times the first moment again, of course, and there's b to c, sorry. Right, this is coming from these 2 bits. And then I'm going to get another contribution that comes from the single edge in the middle, right? So in that case, I'm just taking the 2 moments, so I get the first moments. Here I get b to c r to the minus alpha minus 1 as before. Well, let me write with the minus d actually, right? And then I have the sum over the ball of, sorry, y1 squared. Right, this is the contribution coming from this edge in the middle. Okay, so it makes sense to put this here, right? And in fact, it makes sense to add a 2 here and a 2 here, right? And then this thing here is then just converging to the average over the continuum unit ball of, let's say, U1 squared. Right, I'm just summing up, I've normalized things appropriately, right? Maybe it's even better to put it here. Okay, so this is just a constant, and so what's happening is that in the limit, if I again use the asymptotics of the first moment, so I get 2 alpha times 2 alpha over r times this quantity that I'm interested in, plus this term that comes from the single edge, right, which is just a constant over r times r to the alpha plus 2 minus 1. Sorry, the minus 1 I already put. Okay. Right, this is just because this gives me 2 alpha, I have a minus alpha here, so I'm just left with 1 copy of alpha. This 2 was from here. Okay. So of course, this exactly puts me in the position to apply the lemma, right? So, here the coefficient of the self-referential term is 2 alpha. The driving term is, well, it's not just regular varying, it's just a power, but it's the index is alpha plus 2, right? So, when alpha is larger than 2, then this guy wins, right? When alpha, right? Now, when alpha is less than 2, this guy wins. When alpha is equal to 2, there are log corrections, right? So this is actually just saying again, you can really see this transition between effectively long-range regime, effectively short-range regime in high dimensions when alpha is 2, just from these ODEs. Okay. So in particular, yeah, and actually, sorry, one thing I should have mentioned before when we were talking about the volumes. I was saying that this ODE you cannot extract the asymptotics from, but you can if you know that the errors are small enough, right? So if we just write this out again, do a usual thing, give the error a name. Let's say A over R times F, right? Of course, the nice way to write this is as the derivative of the log, right? So you get log F is a constant plus, well, if I integrate A over R, I just get A log R. And then I have this error term. Okay. So in particular, F is constant times R to the A times this exponential of the integral. Okay, so if I know that delta R goes to 0 fast enough that delta over R converges, right, then this just becomes a constant in the limit. Okay, and in fact, what happens is that in the high dimensional regime, the errors are always small by powers, right? So certainly if you're small by a power, then if you multiply by 1 over R, you become integrable. And so in high dimensions, you'll just get that this just becomes a constant. The second moment's growing like R to the 3 alpha. Okay? Okay. And, a similar thing is happening here. When alpha is larger than 2, the errors are actually, this second term is actually small by a power, and so in the end, it just gives you a constant. Okay, so what you get is that when alpha is larger than 2, so in that case, you're pegged to this driving term, you get that this is asymptotic to R to the alpha plus 2, times some explicit constant. And when alpha is less than 2, you get that this is asymptotic to R to the, sorry, this is the wrong way around. No, sorry, it was the right way around. Yes. Yeah. When alpha is bigger than 2, this second term is negligible. You get R to the. Okay. And there's a log in when alpha is equal to 2, as you can imagine. Okay. Good. So eventually by following a similar procedure, but you look at more and more moments, eventually you get the full superprocess scaling limit of the model. And in fact, in terms of like the pure math techniques, there's not much more to say than what we've done so far. You keep writing down asymptotic ODEs for more and more moments. You end up getting these recurrence relations that come from using the lemma, basically, because you get the driving, sum of the different driving terms times something, and you have to solve these recurrence relations. But other than that, it's similar. Okay. Now, one nice way to think about this is in terms of what's called the radius of gyration, right? So what I can do is I can divide by the first moments and take the square roots. This is what's called the L2 radius of gyration, right? And of course, what do I get here? I get R here, And here I get r to the alpha over 2. Okay, so why is this a natural quantity to consider? Well, it's giving you a measure of how far away a typical point is in a large cluster. So equivalently, if I look at the size bias measure, then pick a point uniformly at random in the cluster in the size bias measure, it's telling you the L2 norm of how far away that is. Oh, sorry, let's say in the Euclidean distance. Okay, and so this radius of gyration is one of several notions of the correlation length of the model. So, I think I mentioned before, there's this sort of vague notion that when you have an off-critical model, and in our case, we're getting something subcritical by taking beta equals beta c, but then introducing this cutoff, there should be a characteristic scale above which the model no longer really behaves in a critical way. And there are a number of ways that one might try to define this, and they're not obviously equivalent. But one thing that is maybe not the first thing that you would come up with, but tends to be quite a useful definition, is this radius of gyration. Okay? And the way you should interpret this, and I should say in the case alpha equals 2, it's larger than r by a log factor. So what's happening is that in long range, at least for the models of high and critical dimension, is equivalent to this radius of gyration being big O of r, So in other words, in fact, this is very reasonable. So if you think about what it should mean to be effectively long range, it should mean that if you have 2 points, faraway points, and you condition on them being connected, the path between them should be like some levy-like thing. It should have discontinuities. In other words, you should see edges of the same order as the distance of the 2 points in the path, right? That's like reasonably what it should mean to be long range, It should mean that in the scaling limit, you still see long edges, right? So that should mean that if you add this cutoff in, you should start to feel the effect of that on the same scale where you did the cutoff, right? And that's kind of what this is saying. So it's a characterization of being effectively long range in terms of the correlation length when you introduce the cutoff is of the same order as the scale where you did the cutoff, okay? And basically what we do is we take this to be the definition of being effectively long range. So, earlier I wrote this theorem about low effective dimensions on the board, and I said, if the model is effectively long range, then blah, blah, blah. This is the definition, except not quite. So for technical reasons, it's convenient to work with the LP version of the radius of gyration. And really, the exact definition we take is that the LP radius of gyration is order r. What's the constant might depend on p for all p. And this we also have, is true for the high dimensional and critical dimensional models exactly when it should be true, i.e. when alpha is less than 2. Okay, and this is what we take to be the definition. So again, this is maybe not the most natural definition, and it would be nice to show that it's equivalent to other ones. So one other one I just mentioned is this thing, if you condition on 2 points being connected, you should see a macroscopic edge in the path between them, right? I mean, I think that should be equivalent to this. I can prove some things in that direction. It should be equivalent to the scaling limit containing discontinuities in it, right? Good. Okay. So I have 3 minutes left. So I can either tell you 3 minutes about low dimensions or 3 minutes about the critical dimension. Maybe let me talk more about the critical dimension because we've already laid a lot of the groundwork. So what we saw in the critical dimension is that all of the log corrections, all of whatever is complicated is just entering in the second moment. That's the only time we get this sort of badly behaved OD that's not robust to errors, okay? And basically what we need to do if we want to compute the logs, we have to find out what is the second order term in this asymptotic expansion, right? So the key thing is to say, if we look at the derivative of the second moment, so we know that the first order contribution is 3 alpha over r times itself. And we need to know what is the asymptotics of the correction to this. And the theorem is that it's asymptotic to the following. So square of this divided by r to the d, let's see, hopefully I'll get this right, times the cube at the first moment. I should say, here I have a 1. Right, so it's this plus lower order or higher order terms. I always get confused about that. I guess they mean the same thing. Okay, so okay, so how would you why is there are two things to explain. What do you do with this once you have it? And there's also the question of like how would you prove such a thing? And one interesting thing here, by the way, this constant c is an explicit constant determined by the scaling limit in a moderately but not that complicated way. It's actually something to do with the probability that a Levy process run for a gamma 4 random time belongs to the unit ball at that time. So anyway, these are explicit things. And again, it's a feature of these things that you somehow really have to compute everything to get it to come out at all. Like I don't know ways of just getting the right power of log without computing all these constants that are not really important. Okay. So if we look at what this means in terms of the function, it's like this ODE. Again, with some error here. F squared over, and of course we know the asymptotics of this, right? It's 3 alpha. So, and I'm in the case where d is equal to 3 alpha. So I get r to the 6 alpha here. Right, and we can see our function is roughly growing like after 3 alpha. It's regularly varying with next 3 alpha. So this term here will be slowly varying at that point. Okay, and here's your ODE, your next piece of ODE homework is that this ODE is enough to determine the asymptotics of f. Its f is asymptotic to some constant, which again is actually explicitly determined by this constant, times r to the 3 alpha over square root log. Okay, and roughly speaking, the reason why you get a square root log is because then when you square it, you get a 1 over log. And then, we saw when we solve the ODE this way, right, we get the integral of 1 over r log r, right? So we get a log, but then we're exponentiating it, so we get a log. So, in other words, if you expect f to have any power of log, not knowing what it is, it has to be 1 over square root log in order for when you do this manipulation to get a log power at all. Okay. Okay, so how do you prove such a thing? Well, you just apply exactly the same method we've been using over and over again. So what you do, you write down an exact expression for this error, which is a bit of a mess, and then you differentiate it. You write down an asymptotic ODE that it satisfies, and eventually you manipulate things until you're in the setting where you can apply this lemma. Right, so what that gives you, very similarly to how we saw that the value of the third moment, right, was like determined, like it could be expressed in terms of the second moment in this simple way. The same thing happens, but where you get that this error term, this complicated thing, can also be expressed in terms of the second moment, and it's exactly what gives you this. So again, you just write down the asymptotic ODE, use your ODE lemma, get a relationship between the thing you're differentiating, or the thing you, sorry, the thing you were originally differentiating and the thing that you're now differentiating, i.e. the error term. Okay. So I think I'm out of time. So yeah, thanks for your attention across the whole week, and it's been very nice being here. Yeah. Yeah. Oh yeah. Right. So, yeah. So it's a nice story. So I mentioned we proved this bound last time, or at the beginning today, that was like the largest cluster in a box. It has size at most r to the d plus alpha over 2. And it turns out that this is sharp in low dimensions and it's not sharp in high dimensions. And moreover, if it's actually little of that, then that is a sufficient condition to run all this analysis. So the point is basically, you can kind of do an analysis by contradiction. So the key thing you want to prove is that in low dimensions, the largest cluster actually has that size r to the d plus alpha over 2. Again, then you've computed some interesting exponent, in this case, an exponent that's not the same in high and low dimensions. And then once you've done that, you can imagine you can do more things. And the point is, you know that it's at most that, that's always true. So you just need to show it's not little o of that. But if it is little o of that, then you can run all the high dimensional analysis, and eventually you just get false conclusions. So it's sort of an interesting thing where you can analyze low dimensions by using the high dimensional method in the context of a proof by contradiction. Yeah. Yeah, they're very robust. So actually, if you look at my paper, I have quite a large class of J's that you're allowed to use. And I would guess that you can change it a lot more than that. In fact, in high dimensions, it's really, I mean, I didn't write the paper this way, but you don't even need the geometry of ZD. You have any transitive graph where it's something like it's some weak LP condition, like not being in weak LP condition for J. So it's something like if you look at the number of x's where J0x is at least epsilon, right? And you look at the rate of growth of that as epsilon goes to 0. If it goes to 0, like a large enough power of epsilon, then you can use, and basically what you'll notice is that whenever we're using the ball here, we never really used that it was a ball, right? It could have just been the super level set of J, and it was just something about its size versus the comparison between the size of this and the integral of the tail of J. Yeah. So yeah, in particular, you could have very anisotropic, like maybe you're only allowed to make long jumps along an axis or something. And in some situations, you'll be able to analyze that.